Hello, welcome back, everyone. We are on chapter 17 in Fundamentals of Inorganic Glasses, which is devoted to the topic of chemical durability of glass. Last time we covered glass surfaces and how the structure and properties of glass surfaces can be different than that of the bulk of the glass. We also covered how water molecules can interact with glass surfaces, making either fizzy-sorbed molecular water on glass surfaces or chemisorbed water in which the water molecule is broken up and forms hydroxyl groups on the glass surface. Today, we are going to take that one step further to study the durability of glass with respect to various chemicals. We'll look at the corrosion behavior of glass in water, as well as in an acidic environment and a basic environment. First, what is the chemical durability of glass? The resistance of the glass surface to chemical agents, especially to fluids, is commonly encountered during use of glass products, whether it is glasses that you drink out of that may have acidic beverages or being exposed to harsh chemicals in a dishwasher, glass packaging that is used for the storage of medicine or any other type of fluid. There can be interactions between that fluid and the glass surface, and that can lead to corrosion of the glass surface. This is one of the most important characteristics to be considered for many applications, even something simple as glass windows. Chemical durability is very important for them because they are exposed to a humid environment. They may also be exposed to acid rain, and it is important that that the reactions between the humid environment and the glass surface are minimized. Most silicate glasses do have excellent durability. Most silicate glasses have molar concentrations of silica of at least 70%. That makes them have very good chemical corrosion resistance overall. Of course, some are better than others. A typical borosilicate glass has better durability compared to a soda-lime silicate glass, and fused silica, pure SiO2, has some of the best durability of any glass. So white deposits on windows and household glassware after repeated dishwashing can result from reactions that occur between glass surfaces and fluids that one may think are apparently harmless, like water. Um, and in another application, glass can actually be used for immobilization of radioactive waste. And for that application, the chemical durability of the glass is the single most important property. Basically, for nuclear waste immobilization, the high level and low level radioactive waste is incorporated into the glass structure and then stored underground for a very long period of time. And it is essential, it is the single most important property of that glass to make sure that it is resistant to any type of corrosion from the environment over a very long period of time. And just from a very everyday point of view, a practical point of view, beverages like beer, for example, simply do not taste as good out of metal cans compared to glass bottles. That is just a fact, and that is because the interaction between the beverage and the glass container is significantly less. Now, when we consider the chemical durability of glasses, there are two different classifications. There is leaching and dissolution. And we need to use this terminology when studying the durability of glasses against fluids of various pH, including water, weathering of glass over time, especially in a humid environment. And there are two primary mechanisms of attack by the fluids on the glass surface. The first is leaching, and leaching refers to the removal of mobile ions out of the glass surface. For example, modifier ions like sodium may have greater mobility compared to network-forming ions like silicon, and therefore it may be easier to leach out the sodium ions compared to the network formers. So this is called leaching, and leaching occurs at very different rates for different elements in the glass. The second mechanism of corrosion is dissolution, also known as etching of the glass network. And this is removal of large parts of the glass network itself. This is taking out some of the glass network formers. And this can either be uniform, meaning that it takes out the ions from the glass surface in proportion to the molar concentration of the species, or dissolution could also be preferential, in which case certain species are dissolved out faster compared to others. These plots show the reaction of water molecules with glass surfaces. You can see a silicate glass surface here on the left, and this is a computer simulation of water molecules coming in and binding to the glass surface. There's two types of binding possible. One is chemisorbed water. With chemisorbed water, the water molecules actually break up into OH groups. Those OH groups bond to dangling bonds on the glass surface, and they can form these silanol groups. So it would be a silicon bonded to an oxygen, bonded to a hydrogen. That is a silanol group. And this is chemisorbed because there was a chemical reaction between the water molecule and the glass surface. The other type of bonding between water and the glass surface is through physisorb adhesion, and this occurs through hydrogen bonding. With physisorb bonding, the water molecule does not dissociate, so it stays as a water molecule, and it just exhibits hydrogen bonding between itself and the surface of the glass. So the left-hand figure shows the interaction of water with silica glass. It is a very similar story for multi-component silicate glasses, as shown on the right. Here you can again see the presence of both physisorbed and chemisorbed water on the surface of the glass. And what this is also showing us is that there is some surface region of the glass, say a few angstroms or nanometers at the surface of the glass, where that structure is modified compared to the bulk structure of the glass. And as that glass structure interacts with water or other species, this interaction layer can grow, and we can have a layer near the surface of the glass that has a modified structure compared to the bulk. So let's consider now the dissolution mechanisms in single component glasses. If we consider SiO2, which is a very highly corrosion resistant glass, within SiO2, there is a high activation barrier for bond breaking and therefore a low solubility in either acids or in water. With pure phosphate or pure borate glasses, P2O5 or B2O3, the opposite is the case. Both P2O5 and B2O3 are hygroscopic, meaning that they are highly reactive with water and can corrode quite readily in the environment. So in these cases, the water molecule is attacking the bonds between the cations and the oxygen, and it is interacting with that, creating an altered layer at the surface, and eventually removing the network-forming species from the glass itself. So B2O3 and P2O5 are both readily corroded in a humid environment. This is one of the reasons why common everyday glass products like glass windows, beverage containers, and so on are primarily silicate glasses instead of phosphate or borate glasses, because silicate glasses, due to their much stronger bonding and resistance to attack by water, have much higher corrosion resistance. Now, as a result of leaching and dissolution of silicate glasses, especially multi-component silicate glasses, there is an alternation layer at the surface of the glass, this surface layer that is hydrated. It has physisorbed molecular water, it has chemisorbed hydroxyl groups, it has a series of reactions related to hydrolysis, hydroxylation, leaching out of specific ions from the glass surface that also leads to incongruent dissolution, where certain species are dissolved faster than others. And all of this creates this leached layer at the surface. The leached layer refers to the modified layer at the surface of the glass where the chemistry has been modified as a result of the interaction with water and other species attacking the glass surface. And that has a very different structure and different properties compared to the bulk glass, which is deep enough that it hasn't yet seen this interaction between itself and water. But if we look over time, this leached layer will continue to grow because over time the water is able to penetrate deeper and deeper into the glass network, and therefore this interaction layer becomes deeper. See in part A of this figure, there is a relatively shallow leached layer that has been hydrated. But over time, these water molecules will penetrate further into the glass, and a lot of the modifier ions get released, leaving behind kind of a skeleton of the silica network. That skeleton of the silicon network can become very hydrated with a combination of chemisorbed and physisorbed water. And that creates what's called the silica gel layer. The silica gel layer at the surface has a lot of these modifier ions removed, leaving behind open space that gets filled by water. And so this is a very wet layer of the glass surface that has low concentrations of modifiers and just a hydrated skeleton of the silicon network. Beneath the silica gel layer, there is a leached layer where there are interactions between water and the glass, but it has not yet completely become a gel-like layer. And then beneath that leached layer is the bulk glass that still has the normally intact bulk glass structure. And what we see is that over time, as corrosion continues, the thickness of the silica gel layer becomes thicker and thicker, and that creates a moving front or a moving interface between the gel layer and the leached layer, and between the leached layer and the bulk glass layer. Now, what are some of the corrosion reactions for silicate glasses? This really depends on the pH of the solution, whether we are in an acidic environment, a neutral environment, or a basic environment. And the mechanism changes depending upon whether it is acidic or basic. So if we look at the reaction here for an acidic environment, if we've got a silicon tetrahedron here that is bonded to, say, 3 other silica tetrahedra, but there is a non-bridging oxygen with a modifier ion here that is labeled as R+, this can undergo an ion exchange reaction with a hydronium ion here, H3O+. Both the alkali modifier and the hydronium ion have the same charge of +1, and there's basically an exchange of the two, where a hydrogen ion from the hydronium exchanges with the alkali ion. This creates chemisorbed water on the silicon tetrahedron, forming a silanol group, SiOH. The H plus ion is switching places with the alkali ion. That releases the R plus into solution, and that also converts the hydronium ion into a water molecule. So what this means is that this is a leaching process because it is preferentially releasing one of the modifier ions rather than etching away the network of the glass itself. It is an ion exchange process because we have a one-for-one exchange between the H plus ion and the alkali R plus ion. And this is also leading to a net increase of the pH of the system because we're reducing the amount of either H plus or H3O plus in the solution, and we're taking that H plus out and replacing it with an alkali ion. And so this means that over time, the pH of the solution is going to go up as a result of this ion exchange and leaching process. If we are at a neutral pH, it's a relatively similar type of reaction. The difference here is that we've got the modified silica part of the network here with the exposed alkali ion interacting now with a water molecule, so H2O. It is again a leaching process that is facilitated by ion exchange, where one of the H plus ions from the water molecule switches places with the alkali ion. That forms this silanol group in the glass, releasing the alkali ion in the process, and then releasing an OH group. Again, this is ion exchange that accompanies the leaching of the alkali ions out. And again, this reaction increases the pH of the solution because we are now replacing a water molecule with an OH group. Now, once we get into a basic environment, this is where it starts to attack the glass network itself. So, for example, if we have some silica unit here in the glass network, this is going to react with an OH group from this basic solvent that it is in, and this actually snatches off an entire silicate tetrahedron from the glass network, forming this H3SiO4 minus group, and basically taking away one of the tetrahedral units. So once we get into a basic pH, the type of attack changes from being leaching to being etching, because instead of plucking away individual modifier ions, it is attacking the glass network itself. It is etching away the glass network. So for silicate glasses, in acidic and neutral environments, the primary mechanism of attack is leaching, and in a basic environment, the primary mechanism of attack switches over to etching. This shows some of the details of the acid reaction mechanism here, showing an example with an alkali modifier here, sodium, and also with an alkaline earth modifier, barium. It is the same thing in both cases. The difference is that the barium has twice the charge, and therefore for each barium that ion exchanges, it requires 2 hydrogen ions to charge balance the 2+ charge of the barium, whereas with sodium, it just requires a single H+ atom. In both cases, it is an ion exchange between H+ and the modifier ions, and in both cases, the pH of the network increases as a result of taking out H+ from the solution and giving either an alkali or alkaline earth ions instead. So in either case, this is an ion exchange mechanism, which is a type of interdiffusion mechanism. In both cases, it is preferential leaching of the modifier ions out from the glass network. This leads to in-depth hydration because as this reaction proceeds deeper and deeper into the surface of the glass, the water molecules can penetrate deeper and deeper, which leads to greater hydration layer. And this means that there is an altered surface layer that forms that is hydrated. This is what happens in acidic environments, the only exception being hydrofluoric acid, and that is because hydrofluoric acid is so strong that it results in both leaching and etching mechanisms at the same time. HF is the single most effective acid for corroding away all glass, and that is why it is used as a cleaning acid for platinum crucibles, for example, because it will etch away all of the glass that is on the platinum crucible. Now, when we go to the base mechanism here, you can see a visualization here of the SiO4 tetrahedron, and then this is reacting with the OH species from the glass, and it is attacking the bridging oxygen bonds between the tetrahedral unit and the rest of the bulk glass structure, and that results in a liberation of the tetrahedral unit, which then goes off into solution. And this actually etches away one layer of the glass structure. So in a basic environment, this is dominated by network dissolution, and this would tend to be congruent dissolution based on whatever chemistry of the glass is left, meaning whatever chemistry is there, that's what gets released into the solution at that point. This results in a net weight loss of the glass because entire parts of the network are being taken away. This etching can also lead to pitting of the glass. So what might have been initially a smooth structure can develop small pits as a result of preferential reactions in certain sites. And this also leads to a silica gel formation due to saturation with respect to silicic acid that forms. Now, one of the interesting things about the reaction of glass surfaces with water is that we can start off with an initially acidic or initially neutral pH, And as a result of that ion exchange reaction, that increases the pH of the solvent such that it eventually becomes basic. So, for example, there's an ion exchange reaction here between the sodium ion and the H plus ion. The H plus then bonds to the silicon network, forming the silanol group, releasing the sodium ion into solution. And what was once a neutral solution here with an H2O molecule, what is left is the OH minus anion. And so our initially neutral pH has now become basic. And what this means is that there is a two-stage attack on the glass surface, where the initial stage of attack in either a neutral or acidic environment is through ion exchange or leaching. But as this process occurs, it increases the pH of the solvent. And then increasing the pH changes the mechanism of attack to then become an attack on the glass network itself. So it's switching from a leaching mechanism to an etching mechanism. This ultimately could be followed by mineral precipitation, because if we reach the solubility limit of whatever species is being removed from the glass, upon reaching that solubility limit, we can have precipitation of minerals that form. And the kinetics of this process are a function of the interdiffusion rate, solubility, local pH, solution volume, etc. So when we consider weathering of glass, the glass corrosion in a humid atmosphere by reacting with water environment, this is a function of both the temperature of the system as well as the degree of humidity. There are two stages to this attack. Stage one is an ion exchange or leaching attack of mobile alkali with H plus or H3O plus. This forms an SiO2 rich layer at the surface, with potential for an increase of the pH under static conditions. This stage one leaching attack is followed by a stage two attack, which is etching or dissolution of the silicon network. And this tends to come into play at pH values greater than about 9. This leads to degradation of the surface itself and formation of insoluble precipitates. These plots show the mass of silica that gets released as a result of corrosion on the top, and then the mass of the glass overall that gets released as a function of pH. The open circles show the mass of sodium oxide that gets released versus the mass of silica that gets released in a sodium silicate glass. And what we see is on the lower plot, at lower pHs, so at pHs below 9, by far the greatest attack is on the sodium oxide itself. So in the acidic and neutral regime, even into the slightly basic regime, sodium is what gets removed preferentially from the glass. And it's only when we get above a pH of about 9 that the basic solution attacks the network itself, releasing considerable amounts of SiO2 at that point. You can see that also reflected in the upper graph, which shows the micrograms of silica that gets released. At the lower values of pH, there is a very small amount of silica that gets released, but above a pH of 9, where the network itself gets to be etched, that's where we start to get a considerable amount of silica released. Now, when it comes to measurement of chemical durability, there are a couple of different ways to do this. These both involved immersing a specimen of the glass in a given quantity of fluid. This can either be under static conditions, where the solvent is just sort of fixed, the volume of the fluid is fixed, or it can be under dynamic conditions. But in either case, there is a certain amount of the fluid that is allowed to react with a certain surface area of the glass. This is being done under controlled temperature conditions. And then after a given amount of time, a given amount of reaction time at that temperature, some leachate is collected and then analyzed using wet chemical analysis techniques such as flame emission or induction-coupled plasma analyses. These experiments then would give you the weight percent of leachates that come out of the glass, and that can be then analyzed as a function of time and temperature and glass composition or solvent chemistry as well. So these experiments themselves can be conducted either on a bulk specimen of glass or on a pulverized powder. The question of whether to use a bulk glass or a powderized sample really depends on the corrosion rate of the glass that is expected under those conditions. If the corrosion rate is expected to be fast, then a bulk sample will be fine because that has a lower surface area to volume ratio. However, if the glass is expected to have a high corrosion rate, then it is beneficial to pulverize the glass into a powder first, because that increases the surface area to volume ratio and therefore would increase the rate of chemical release as a result of the reaction because of the greater exposed surface area. The glass surface composition, as we know, is generally different from that of the bulk, and that can be a result of volatilization of particular species during the glass melting and forming processes. And hence, if the durability of the as-formed surfaces is the issue, then the experiments are best conducted on specimens having as-formed surfaces. So that is another factor to keep in mind, is what type of surface do you want to study in these corrosion experiments, and make sure that the corrosion experiment is designed to probe that particular type of surface. Now, as I mentioned, corrosion experiments can be conducted under static conditions or under dynamic conditions. If it is under static conditions, then there is a fixed quantity of the fluid medium. If it is done under dynamic conditions, then the fluid is flowing over or flowing through that medium. So in a closed medium or a static experiment, the pH increases with time because of the extraction of alkalis, and then that pH, that higher pH encourages dissolution of the network. So in a static experiment, you can explicitly see the two stages of this corrosive attack. Stage 1 dominated by leaching and stage 2 dominated by etching after the pH increases above about 9. However, if we do dynamic or open corrosion experiments, then fresh fluid is continuously flowed over or through the sample, and therefore the pH of the experiment is a constant because it is continually being refreshed with new fluid. So these figures show schematic diagrams of either a static corrosion experiment on the left or a dynamic corrosion experiment on the right. In a static corrosion experiment, this is done in a fixed volume of solution here, where the glass powder or glass specimen is immersed in this constant amount of solution. Over time, the solution reacts with the glass that can form a modified altered layer at the surface as a result of that reaction. And then different samples of the solution are taken and analyzed to see how much of each species is being released from the glass powder into solution. And of course, since this is fixed, the pH will evolve over time and the mechanism of attack will also evolve over time. On the right-hand side, in the dynamic corrosion experiments, we have solution that flows through the glass powder. Usually this glass powder would be in some sort of vessel, and then that is connected to tubes where the solution flows in and flows out. And then the solution is collected at the output and then analyzed to determine what are the concentrations of ions that get released. This is the more common way to conduct dynamic corrosion experiments, but another way would be to flow the solution onto the surface of the glass and then collect it. And this latter case would be used for less chemically durable systems where you've got a higher corrosion rate and therefore can analyze the solution easier in that case. The plot here shows the concentration of hydrogen that gets released into the glass. This is showing the ion exchange reaction that occurs between hydrogen and sodium as a result of that ion exchange reaction. This experiment was conducted on soda lime silicate glass. that was immersed in water at 90 degrees Celsius for 560 hours. And the interesting thing that you'll see is that the amount of hydrogen here is significantly greater than the amount of sodium. And in fact, it is almost about 3 hydrogens exchanged for each sodium. And what this is indicating is that it's not really an H plus cation that is exchanging for sodium, but really an H3O plus molecule, or which is a hydronium ion. And the interesting thing here is that the hydronium ion has roughly the same ionic radius as, or not much smaller than that of potassium. And so this is showing that it's actually a slightly larger sized species that is exchanging in for sodium. And it's a 3-for-1 exchange of the hydrogens for each sodium. Now that we know how to measure the corrosion resistance of glass, what are some methods for improving the chemical durability of glass? One way is to increase the concentration of silica in the glass or increase the concentration of alumina because those species have more bonds and stronger bonds. Increasing silica is especially effective at improving the corrosion resistance of glass. We can also try to design the glass compositions to reduce the mobility of alkali ions and also reduce the concentration of alkali ions at the surface. Glasses could also be coated and have barrier coatings to impede the approach of the attacking fluid to the glass surface. Some things that we note are that glass products that are silica and alumina rich are generally superior for chemical resistance, and the chemical durability of soda lime beverage containers is usually increased by adding about 2 to 3% of alumina, because that does lead to a much better chemical corrosion resistance for those applications. All right, that does it for our lecture on chemical corrosion. In the next 2 lectures, we will be looking at chapter 18, which is on glass strength and toughness. We will be covering both the basic scientific principles of glass strength and toughness, and then how do we increase the strength and toughness of glass products. All right, thanks so much for watching. Please let me know if you have any questions, and I will see you next time. Thank you.